Hello, everyone. So as mentioned, today my talk will be about large-scale field delineation. Before I start, let me introduce myself. My name, as mentioned again, is Hrach Asatryan. I'm a machine learning scientist at Delineation, and besides that, I'm a physics master student at Yerevan State University, Faculty of Physics. My specific areas of work are computer vision for machine learning and high energy physics, elementary particle physics, etc. My hobbies, even though you probably don't care, are sports and gaming. So let's just jump right into the main topic. So first of all, what is field delineation? So field delineation is basically just the estimation of field boundaries. This can be done in a number of different ways, either by hand or by automated machines. And it's really a very broad definition. It's just the estimation of boundaries. So why do we need it? Well, given that modern agriculture is still field-based, so everything is on the field level, usually farmers don't collaborate as much. Even if they do, everything is specific to the fields. If we want to use some tasks to help farmers, we need to be able to delineate the fields and have each specific field. So someone might wonder, who cares about agriculture? Well, good question. But given the environmental and the geopolitical chaos in the world right now, global food shortages are becoming now more scary than in the past, I don't know how many years. So investing in agriculture is key to solving some potential issues that might come back to bite us in the future. And what does AI have to do with agriculture? Well, AI has infiltrated basically everything at this point. So given the rise of machine learning, AI, again, has become integral for the development of agriculture. So aerial imagery is used by companies like us to maximize yield potential, crop health, and assist farmers in basically having better farms. So now that these are out of the way, what is our solution to field delineation? Like, as I said, you can do it in automated pipeline. That's what we use. We use an encoder-decoder-based deep neural network to predict delineated fields using aerial imagery. So I'll go step by step over our workflow, which is firstly creating the data, then creating the model, post-processing the model's predictions, and going to a larger scale. But as of now, this is just the gist of it. We want to use a deep neural network. Okay, so if we want to use machine learning and neural networks, we need data. So section 1, data collection. What data do we need? Well, we want to predict field boundaries, field extents. So obviously, we need the masked annotated fields of areas. This is the picture on the right. So this is the annotated mask of the fields in a given area. Now, besides that, we obviously, since we wanted to train with aerial imagery, need some aerial imagery of large-scale lands. So basically, field-heavy areas, something like this. So all we need essentially is images of some areas that have a lot of fields, like this one, and some annotations of those areas to be able to train the model on. So input and ground truth. So where do we get this data from? Let's start from, I guess, the harder part, the field data. So for the field masks, obviously, like none of you, I think, have that good an idea where to get annotated masks of fields. So this is the harder part, and we have chosen 3 sources here. The first one is the French government's yearly release of their field data. I'm not going to try to pronounce this because I'm going to butcher it horribly. But it's basically the French government's yearly release of all fields in France. So this image was from the RPG data, and it's a really good data set. It's dense, it's clean, it's accurate. The only downside, it's French. Now, no offense to French people, but our interests lie in the American domain because our customers in America are in America. So using French data, there's a bit of a domain shift. Having French data kind of hinders that. But it's a very good data set regardless. In most applications of field delineation, this is the go-to data. So, okay, we want American data. American government has their data too. This is called the Common Land Unit data, or CLU for short. The data set is very dense. The data is American, freedom. And so it's good in that sense. But the downside is that it's an old data set because it's been privatized by the government since 2008. So the best data you're going to have is from 2008, and obviously a lot has changed since then. And the data has a lot of false positives, which isn't necessarily an issue with the data set, it's how we use it. Because Common Land Unit, I'm guessing some of you wondered what that is. It's basically the definition of something like a farm, but that definition also includes stuff like lakes and forests. So those are also annotated, and thus, if we use this data, we have a lot of false positives. So all in all, we have this data. It's an American data set, but it's not particularly, it's not of good quality. And then the third perk of being from IntelliNet, we have data annotated by our annotators. So this data is extremely clean, it's fresh, and it's accurate. So it's basically perfect wherever we have it. But the thing is, it's only data of our customers' fields, and thus it's sparse and it's smaller. So having a large-scale training only on it is practically impossible. And what have we chosen? Well, we've chosen two data sources, actually. And I'll get into how we use the two together in a bit. But we've chosen the French RPG data and the IntelliNet data. So when I say our data or IntelliNet data, I'm going to mean this. And when I say RPG data, I'm going to mean this. Different experiments have been done. This choice of data sources is the one that yielded the best results. And here I've brought some examples of the two data sets. So given an RGB image, this is the French RPG data. You can see what I meant. It's really clean, it's really accurate, and it's very dense. And this is our data. It's, again, clean and accurate, but it's very sparse, as you can see, and that's just fundamentally how the data is. So now that we got the data sources checked out, let's talk about the aerial imageries. We mentioned that we want to train on aerial imageries, and we basically, given what data sources we chose for the masks, we have to choose some aerial imagery source that basically covers the entirety of the United States and the entirety of the French Republic. That's a huge area. This basically means imageries that cover the entire world. Here we have had two choices. One is Sentinel-2 imagery. Sentinel-2 is a satellite that gives free imagery on 10-meter resolution, 10 to 60. We use 10-meter resolution, basically anywhere. So this is the first choice, and the second is Mapbox, which is not a free provider, but another perk of working at IntelliNet, we have a Mapbox subscription. So we were able to use Mapbox API to get their imageries. Now, Mapbox resolution, they differ from all the way up to tens of thousands of kilometers to even a couple centimeters per pixel, even lower than that. So Mapbox imageries are, like, as you can see, a bit cleaner. We have more freedom. So given that we have access to it, we've chosen to go forward with Mapbox data. And now that we have the data sources figured out, let's move on to the model creation. So we want to train a model. As mentioned, we need an input and we need a target. So as the input, we have chosen the RGB image, as I said. This is what Mapbox provides. And as the target mask, we have chosen 3 masks to predict. So first one is the boundary mask, where 1 denotes the boundary of a field, and 0 denotes not the boundary of the field. The extent mask, which is basically the field, 1 denotes a field and 0 denotes not a field. As you can see here, so these are the fields. And then the third one is the distance mask. So what is the distance mask? I guess you can figure it out already. It's basically how far a pixel is from the boundary. Pixels that are furthest from the boundary, they have the higher values. So this is, for instance, in the middle, it's 1, and near the edges, it's closer to 0. So in one of our sources that we've used, this is proven to be beneficial choice of target masks. We have tried some experiments without using the distance mask. While it may seem counterintuitive, like why would you use it? It actually improves results in general. So now let's talk about the thing that I mentioned before. So domain shift. We have French data, but we want to do inferences on American fields. How do we train a model using this? So in this source paper by Franz Waldner and Shering Wang, they discussed this issue while trying to train on French data and predict on Indian fields. So they have the same issue, just different countries. The French data is available for everyone, Indian data is not. And as you can see here, there is a disparity between field sizes in France and field sizes in India. So whatever way you go, there is going to be a domain shift if you just try to train on French data and predict on American. How do they tackle this problem? They use transfer learning and weakly supervised learning. So what is weakly supervised learning? Let's talk about that for a bit. So basically, the thing is, since there isn't a lot of data in India, they had to annotate it by themselves. Now, data annotation costs money, it takes time. So you have to, if you have limited resources, you can't, I don't know, mask all of India, you have to make a choice. Do I annotate a lot of images that are sparsely annotated, like this one? So we have this image, only a few fields have been masked and annotated. Or do I have a few samples and annotate it densely? So something like this. If you have limited resources, that's the choice you have. So in their paper, they say that using an approach like this, where you annotate a few fields and mask everything out, it's better than having a few examples of densely annotated data. So in their case, they did this because of limited resources. But remembering what our data looked like, this kind of looks like our problem. We come from a different point, but we arrive at the same problem. And they proved that using this approach is beneficial, actually. Not even it's okay, it's beneficial to use this. And they also use transfer learning. So basically, this is the approach they use. They train on multi-planet mosaics, feed that input to a neural network. In their case, they use a fractal ResUnet. They train that one on French government collected boundaries, so the RPG data. Then they use some other imageries for India. This doesn't particularly matter for our case because we just use Mapbox in any case. And they transfer the weights of the French model to the Indian model, and then they train on these masked inputs on the Indian data. So they train on densely annotated French data, they transfer the weights to a different model and fine-tune that model basically using weakly supervised learning with masked Indian data. So that's the approach they use. A different problem that I mentioned and that they've tackled is the difference between field sizes. Like as I mentioned, you can see here it's about 6 times, French fields are about 6 times larger than Indian fields. And so that's going to give a difference on your imageries. What they do is they downsample French imagery. So the average pixel sizes of the fields are the same for Indian and French data. Obviously, this works. If you downsample, you go higher. Obviously, the real size of the fields doesn't change, but the pixel sizes on each image, pixel areas, they get smaller. And using this technique, you can see the difference here has closed up. The French and Indian field sizes are basically the same size on average pixel-wise. So this is another thing that they use, down or upsampling in our case, since American fields are larger. The initial data to have the same pixel size improves results. So let's circle back to our data. Everything was just a citation. Now let's come to our data. Our data is also sparse, as I mentioned. So this weakly supervised stuff seems to be suited specifically for us. But there's one very key difference. Here, as you can see, if you look closely, they have field interior, not in field, and masked out. So they have negatively annotated parts. Even though it's mostly masked out, the parts that are annotated, have some negative annotations. In our case, we only have the fields of our customers. So fundamentally, we don't have any negative annotations. If we take the annotations that we do have and mask out the rest, we're basically going to have 100% positively annotated data. So this is a key point, and this is a problem, but regardless, we're going to try this approach, and we're going to try to mitigate this later. And for this field alignment, I've called this, so the field size, symmetry stuff that they try to get the same pixel size. We've done this as well. American fields are larger on average than French fields, and thus we have trained the French dataset on a mix of Mapbox Zoom level 13 and Zoom level 14 resolutions. So Mapbox, as I said, they have a number of different resolutions. They're just numbered. The resolution we want, they're called Zoom level 13 and 14, and here are the resolutions. So it's about, the first one is 1.6 meters, and the other one is 0.8 meters. Now that we have all this sorted out, this is our final pipeline, basically, of training. And here we tackle the problem of having no negative annotations. What we do is, during the end of the training scheme, we do a very small training on the French data, again. So basically fine-tuning, very small. I can't stress this enough, like 1 or 2 epochs. This is just for the model to see some negative annotations and be able to predict stuff like forests and lakes as negative. If not for this, the model performs very well at delineating everything, but it treats everything as a field. So it will be very good at segmenting a lake from a field, but it's going to say they're both different fields. Going over everything, we use the French Zoom 13 and Zoom 14 data. We train a model using both of them and get this French Zoom 13.5, let's call it, model. We transfer the weights like they did in their paper, and we fine-tune using so IntelliNair's Zoom 13 model data. We get this model that is very good at delineating everything, but predicts positive everything. And then we do a very small fine-tuning using Zoom 14 French data. Anything could go here, 13 could go, both could go. We just do a fine-tuning using Zoom 14 French data, and we get our final model. So this is the training scheme that we have chosen. The paper suggests this much, so without this fine-tuning, but given our problem, this was something we had to add. And these are the final model performances. So the metrics here, the boundary metrics might be low, like if you just look at it without context, but that's just fundamentally how it's supposed to be. You can imagine if you have a boundary mask and another boundary mask, if you try to calculate the metrics and, I don't know, the predicted boundary mask is shifted by a single pixel, like boundaries, look at what they are. If everything is shifted by a single pixel, there's not going to be any overlaps. So the metrics are going to be low, and that's just a fundamental property of boundary data. And as such, these might seem low, but they're actually pretty good results. And you can look at the field metrics, which are pretty high. These are the results of the final models of this one after all this training. Now we have a model that is able to predict fields and boundaries. Great. So before moving on, let me stress a key point. under-segmenting is worse than over-segmenting. Why is that? If you have a field, let's say a single field, if you predicted as two separate fields, it's easier for a person to just combine them. But if you have two fields and the model predicts them as a single field, it's very hard to, so you basically have to do whatever it is you're trying to solve using machine learning. You have to go and delineate it again. So you haven't solved anything. So in this task, over-segmenting, so splitting a field into a couple smaller fields, is better than under-segmenting. So that's a key point that we want to remember going forward. Now, our model is very good, as you can see, at detecting field and boundaries, but it's very bad at closing boundaries. So if we want to get field instances from this, you'll see that some fields are going to connect by a single pixel, like here. It doesn't close, and this is a single field. So this is a problem, but there are specific techniques that are used to tackle this. And the technique used is called watershed segmentation. Watershed segmentation is a pretty common technique in instance segmentation. You can see on the bottom, this technique is used to, like with 100% accuracy basically, they segment these coins from each other, and it's a very common technique. What is it? Now, any grayscale image, you can treat it as a topological image. So you can view it as a map, where higher values are like mountains and lower values are like valleys. So if you have a probability map where you have values from 0 to 1, you can imagine that as a topographical map. Now, the basis of watershed segmentation is, let's treat this map like an actual map. Let's take the local minimi, and let's start filling them with water. So the water levels will rise, as you can see from here. It'll rise from here. Then on this line, the two will start to spill into each other. The point is, as soon as two neighboring valleys, they start pouring into each other, you put a boundary there. And you repeat this process over the entire image. So basically, you take each local minimi, so basically something like a point in this field and a point in this field, you start filling it with water. As soon as the water is touched, you put a boundary there. And then you go on doing that for the entire field. And after that, you just take everything, like this is the first label, this is the second label, this is the third label. So you're able to segment the instances from each other using this method. And here are the results. You can see how big a difference it makes. So it's very good at delineating and closing the boundaries and just having different instances for each field. So the watershed segmentation helps a ton, but besides that, we have a couple smaller stuff we do while post-processing. First one is watershed segmentation. That's like a key thing. Without that, our model would not be as good as it is. Then we do something like small field cleanups. So if you look here, I don't know if it's noticeable on the presentation, but there are some like random red dots here. I don't know if you can see it, but like it's a model. It's gonna predict some random dots as fields or boundaries in the middle of nowhere that aren't actually useful for us. So what we do is we just set a threshold and we discard all the fields that are smaller than a certain value. This is just a step for us to actually clean the data up. And finally, after this, we throw away the boundary mask that we have predicted, and we use the boundaries of the field mask. So like the predicted boundary mask you can see here, and I think this one is with the boundaries of the field mask. So you just take each instance, take its boundary, and that's your boundary mask now. This also makes the results a bit cleaner. Even though at this point the boundary mask has lost most of its use, so it's not particularly important. Okay, so now we have a model that is good at predicting the fields and the boundaries of a single tile. Okay, that's great. But how do we move to a larger scale? Like, usually you do these segmentation tasks. Moving up to a higher scale isn't that hard because you can just combine everything. But here we have a specific problem since we're doing instant segmentation rather than just segmentation. Look at these two tiles. They're tiles next to each other. So on the left, one is to the west, one is to the east. And they're split in two. And look, fields that get caught in the middle of these two tiles, so this field and this field, they also get split in two. So if you just do a tile-by-tile approach, like take an area, iterate over all the tiles and do predictions, some fields like this one are gonna split in two. Okay, one might wonder, let's just combine everything that touches each other. Okay, a good point, but there's this little strip of land that isn't part of this field, but it's gonna connect because, like, farms don't have to be rectangular. They can be in all sorts of shapes and sizes, and some fields can touch, even though they're different fields. And if we're unlucky, that this can be directly on this boundary line, and besides that, our model might not predict all the way up to the boundary because it's a model. It might just have a 1 pixel wide gap between the two instances. So just combining doesn't work. So we have a problem that we want to solve from going to a smaller scale to a larger scale. And this is the solution that we've made up. So bear with me. So what we do is for each tile in the grid, so we take an area and we iterate over all the tiles. Now for every specific tile, we do an inference on the tile. And after doing the inference, we get something like this. Then we discard all the geometries that touch the boundary. So basically, we discard this one, this one, this one. Everything that touches the boundary of the tile, we discard it. Right now, we have the prediction of fields that are 100% in the tile. These are not split. These are correct. But we want to predict the fields on the boundaries as well. To do that, we create a larger tile using the tile on the right and the tile on the bottom. So imagine this is a single tile, so this quarter, we create this larger tile, concatenating basically the tile to the right and the tile to the bottom, making it a 2x2 tile, so to say. So we have this larger tile that basically includes all the fields on the right and the lower boundaries. After that, we do inference on this larger tile. So now we have all the fields in a larger area. So if we went by 512 and 512, we have all the fields of a 1024 by 1024 tile. And then we discard all geometries that do not touch this southeast boundary of the original tile. So basically, we discard all the geometries that don't touch from the directions that we made the tile larger. By doing this, we basically have the fields, internal geometries from here, and we have the geometries of its southern and eastern border from here. Now we concatenate these, and we have the geometries of the tile, the internal geometries of the tile and its southern border and its eastern border. Besides this, we remove some intersecting geometries because obviously we do predictions on the same area twice. There might be some intersections of fields that don't quite touch the boundary. We remove these even though those are less of a problem. And right now, for each tile, we have all the geometries except the ones on its northern and western boundaries. How do we tackle this? We don't. For each tile except on the first column and the first row, their northern boundary is going to be a southern boundary of another tile. So it's going to be accounted for using the method that we used. So in reality, we're going to have a single row and a single column that don't have don't have proper predictions for one of their boundaries. So what? If we have a specific area we want to do the inference on, we do it on a larger area and just ignore the first row and column. So yeah, after that, those are the final geometries of an area. So using this method, no matter how large you have your area you can do your inference on, your only limitation is basically your RAM, but you can upload the geometries to a database at any point. You can write them to your machine. So this basically takes some time, but it's scalable. You can go to any scale without any limitations. And here you can see this basically is almost as big as Illinois itself. It's Illinois, a bit of Indiana, some Kentucky and Missouri. So the inference has been done on this very large patch of land using this method. And like this is scalable to an even larger extent. If you wanted, if you had enough time, you could do this over the entire United States. To conclude, we used publicly available French data and our annotated data along with Mapbox imageries for training. We used transfer learning and this method called weakly supervised learning to effectively use both our data sources. And we used watershed segmentation to post-process our predictions because otherwise the instances were incorrect. We created this technique to be able to move to a larger scale. And we used all this to do the predictions on the following area. So these are the sources that we used. As I said, this one is the one with where they suggest watershed segmentation, weakly supervised learning, transfer learning. And this is a Medium article, actually, that basically was a good baseline for us to start our research. Thank you. Do you have any questions?
Thank you. Very interesting talk. I have actually two questions. How does the seasonality affect all of this work? Is there a preferred season, or do you have to do this maybe multiple times a year?
That's something we have discussed. It's something that depends on the season, obviously, because the imageries, it might be easier to tell a forest apart from grassland or a field, depending on its color. But we've used Mapbox, which is actually, I think, an aggregation of different season times. So the imageries are not from a single point. They're this complex mashup of different time stamps. So the seasonality is something that is definitely a point, but we haven't tackled specifically in this research. The predictions were done during, it doesn't matter. So it was done using Mapbox imagery, which is, different.
The combined.
Answers. Yep. Yeah.
And the second question is actually about this slide. When you stitch together these two tiles, is there an overlap or a little bit area that's missing?
No, actually, Mapbox just perfectly goes tile. The way they use you just give a tile number, and their API gives back a tile, and they perfectly follow each other. So there's no overlap.
Just putting together is exactly the same as it can.
You just stitch them together.
Makes sense. Thanks.
Thank you for the speech. I actually have two questions. One is really small. Is the RPG dataset open source?
Yes.
Okay. And the second question is, you said that you can even take the whole image of United States and feed it to your model and it will work, but isn't there an issue with the boundaries getting smaller and the fields getting smaller and you cannot differentiate between
so you mean going to a higher resolution?
Yeah, like there is an upper bound where you can't even
I actually meant like going same resolution, but just a larger area. So you're going to have the fields of the same size just go all the way over the United States.
Okay, like
that's going to take ages. I was just saying there's specifically no upper limit. You can do anything you want. But yeah, realistically, predicting over the entire United States using this method
Yeah,
will take forever.
and also, do you use like a custom model, or it's just like a unit-based model?
We use, so here in the paper, they suggest using a fractal ResUnet. It's their model for, I think, specifically for stuff like this. In our research, we've used ResUnet 34, so a unit with a ResNet 34 backbone. So yeah, any model really works. We did add dilation because the inputs are like so finicky, so having dilation helps. But yeah, in essence, the model isn't critical. Any model having a unit-based architecture will suffice.
Thank you.
Yeah, thank you for the presentation, and it's great work. One question I wanted to understand. So you did this unusual trick of fine-tuning on not the final data set at the end, right? That's a pretty rare thing, I think. And did you try to measure whether you lose anything? Like if you do that, you had multiple metrics, right? Precision recall. So maybe I missed this part. So if these are fields or these are like pixel?
They're the pixel level metrics for the field mask.
Okay, for field mask. Okay, so did you notice any like before you did this final fine tuning?
Well,
you
actually,
had false positives, right? That was your problem.
The thing is, we had more false negatives. So like here, we have a lot of false negatives. We barely have any false positives. And the metrics indeed were very high, but they weren't telling us anything because they were only calculated on positive samples. So it was like unusually high that didn't tell us anything because of how the data was constructed. So there is no way of knowing whether or not the French fine-tune actually damaged basically the positive predictions of our model, but it definitely improves the negative ones.
So you were not able to measure how if it damaged or not? Is that what you say?
We have not measured whether or not this final trick has damaged the prediction of the field specifically. In general, as I said, it improves, but for the fields, I understand what you're asking. We haven't measured it.
Yeah, I think another option that you could try, I don't know if you did, you could simply add like 10% of this French data to your data set. And
yeah, that would, I think, have the same effect. Since this fine-tuning was so small, I think what you mentioned, it could work, yeah. That's something we could have tried, definitely.
Interesting, yeah, it's an interesting thing to do. Like, I wouldn't risk that, but obviously, yeah, if you do it like slow enough and with small learning rate, and maybe you don't do the forgetting. Yeah, thank you. It's very interesting.
Sorry, maybe I missed this part, but do you actually use the images as your input and output, or do you use some kind of representation?
Sorry, can you repeat?
Do you take the images as your input and output, or do you use some kind of representation of the images?
We use just the RGB image as the input, and we use these three masks as target masks. So it's just the image.
Because some of like those images can have some like simple representation in certain bases or something. Do you think that could help you? Because like the regions are, locally they are very constant, or the boundaries are just unions of curves.
It could. We haven't tried anything like that. It's just these as the inputs.
Thank you.
Did you try adding any other features? For example, annual precipitation, or time of year at which the imagery was taken, or distance from urban center?
No, these are just the stuff we've tried. The time of season was something that we've discussed, so it was something that we have considered, but at the end we ended up not using it. So this is all we've used. And the other stuff we haven't tried at all. Yep.
I mean, I'm sure you do use some data augmentation, but have you tried using like some like copy-paste type of augmentations where you take your sparse annotations and put it on some background where there are no fields? Like, have you tried those type of things?
The thing is, for our small data set, our model would usually go in the wrong direction because of these that are annotated as negative.
Yeah, but I mean, you like copy those masked areas where you know there are definitely fields, and you paste it on a completely different
I got
image
it.
where there are no fields.
No, we haven't tried it, but it's an interesting thought. So it basically the where the stuff is, right? So where?
Yeah, like you can just paste it on a lake, let's say.
Yeah, it's definitely interesting. We haven't tried it. It hadn't crossed my mind that something like that could be done. Something we know for a fact that is negative, but it's definitely an interesting thought. Thank you.